Next up is network layer. Network layer provides end-to-end transport thanks to four processes. And it is important to remember these four processes at the network layer. The first process deals with addressing. The second process deals with encapsulation. The third process does the routing, the actual routing for us. And the fourth process performs the de-encapsulation. Starting with addressing, remember it is important that network layer addresses, they should be unique in order to distinguish individual sources and destinations from each other. Different hosts, they need unique IP addresses. The second process in network layer is in encapsulation. Encapsulation, the process of adding headers and sometimes trailers to PDUs. Here in layer 3, we want to encapsulate layer 4 PDU, i.e. layer 4 segment is encapsulated into layer 3. Encapsulation process is pretty much like letter and envelope, that you put letter inside envelope. You encapsulate it. Here the letter is layer 4 PDU segment and the envelope is packet. Encapsulating data, when it is performed in layer by layer basis, it enables the services at different layers to scale without affecting other layers. So services, let's say at network layer, if new protocol comes in, for instance, it can scale without affecting layer 4 or layer 2 because encapsulation happens layer by layer, and for this reason it is independent of other layers. The third process for network layer is the famous one, routing, or the process of finding the best path from source to destination to a remote network. Routing is done by routers, and routers, they implement different network layer protocols concurrently at the same time over a network and use the network layer packet header, thanks to encapsulation, for routing. So packet header or layer 3 PDU header is used for routing in order to select the best path. And fourthly and finally, the encapsulation process is there. We take off the packets from the media, and when we remove the header, we call this process the encapsulation. That means we give the segment, the pure segment, to the layer above network layer or fourth layer. So we already know about layer 1 and layer 2 about Ethernet, the most widely used LAN technology that employs bus topology consisting of a single long cable, let's say, and that single long cable is called bus, or is called channel, or is called either, whatever your term you want to use, to which multiple computers attach. And therefore any host, let's say, can send signal down to that cable, and all attached devices to that cable receive a copy of signal. Thus, Ethernet is an example of broadcast network, and it is of course limited to 500 meters, let's say, with minimum separation of 3 meters between each pair of connection. But when we want to create internetworks, we need the routers. So here we are talking about layer 3 routers. They allow creation of internetwork, and thanks to these four processes that you have seen now, routing can happen, or the process of selecting the best path is doable and feasible, thanks to addressing, thanks to encapsulation, thanks to routing, and thanks to the encapsulation processes. Next up, we want to see the characteristics of network layer. The very first characteristic of network layer is low overhead. Remember, with network layer, we only have functions that are required to deliver packet, and that's it. Because we just want to deliver a packet and we don't want to have any other fancy functions there. Secondly, network layer is known to be connectionless. It's not a connection-oriented protocol. It is a connectionless protocol like snail mail. You have no idea if destination is present. You have no idea if destination is reachable at all. You have no idea if destination is functional. Still, you send and you hope it gets to destination, and that's it. This connectionless characteristic, in fact, contributes much to low overhead for network layer. So when we say network layer or IP is low overhead, one main reason here is the connectionless nature of this protocol. Thirdly, we know IP or network layer as the best effort delivery mechanism. So it's just best effort, that's it. And when we say it's just best effort delivery, we mean that it is unreliable. How is reliability or unreliability defined in this context? When we say network layer is unreliable in this context, what we mean is that there is no capability to manage or to track or to recover from undelivered or corrupt or out of sequence packets. Packets that have been delivered not in correct order cannot be tracked and therefore cannot be fixed or recovered. So what would happen to applications that are, let's say, delay sensitive, or applications that require in order delivery or in sequence delivery of packets? In those applications, the reliability needs to be taken care of by upper layers like layer 4 or application layer, but not in network layer, because we want network layer to stay with low overhead, and that's why we want it unreliable. So there is no tracking feature for flows, no managing feature for flows, for packet flows, and that's why we call it unreliable protocol. It's just best effort delivery, and that's it. Last but not least, network layer is known to be media independent. Doesn't matter if we have wired or wireless media at the end towards physical layer. However, network layer does have maximum size of PDU that can be transported. This is called maximum transmission unit, MTU. So layer 3 does have MTU for packets, for its PDUs, called packets. And maximum transmission unit, MTU, is determined by layer 2. So layer 2 tells layer 3 MTU and its value. So network layer is media independent. However, it does have MTU that is determined by layer 2. Next up is IPv4 and IPv6 headers. So On the right hand side, top right hand side of the slide, you see IPv4 header. Below that you see IPv6 header. 4 different colors. The color code is the violet color. Are those fields that remain the same moving from IPv4 to IPv6. We still have them with the same structure. Then we have gray color. Gray color are header fields in IPv4 that do not exist anymore in IPv6. Then we have sort of greenish color. They are those header fields in IPv4 that they remain in IPv6, probably with different names, but they're the same concept. And of course we have blue color, just the one that you see in IPv6 header. You don't see it in IPv4 because this is the new header field defined only within IPv6. So that is defined with the advent of IPv6 and does not exist with IPv4. What is a header? A header contains the information required to route data on the internet. Header has the same format regardless of the type of data being sent. This is the same for an envelope where the address format is the same regardless of the type of letter being sent with that envelope. So it is important to remember that unlike post office, a router or computer cannot determine the size of a package without any additional information. In post office, the person there can look at a letter or box and determine how big it is. But with this example here, routing, a router cannot. Therefore, additional information is required at the IP layer in order to specify how big, let's say, a packet is. And this additional information is in addition to the source and destination IP addresses. And header can be used for serving this purpose. Inside header, we have fields. Fields, they contain binary numbers. Numbers identify various settings. And those 4 processes that I just explained, they use numbers, these numbers. So numbers are examined by the layer 3 processes. Let's start seeing IPv4 header fields. We start with version, a 4-bit field that identifies the IP version being used. So it specifies if the packet is IPv4 or IPv6. If it is, let's say, IPv6, then this 4-bit binary value is set to 0110 that identifies it is an IPv6 packet. Second IPv4 header field, IHL, Internet Header Length. So a 4-bit field containing the length of the IP header. So remember, Internet Header Length, or IHL, has to do with the length of header. And this size or this length is in 32-bit increments, meaning that if we have the minimum length of an IP header, that is 20 bytes, then we have 5 32-bit increments. So this field is set to 5. If we have maximum length of an IPv4 header, that is 24 bytes, then this field is set to 6 because 6 32-bit increments creates 24 bytes. Therefore, IHL, Internet Header Length, is always either 5 or 6. So this field should contain either 5 or 6. The next header field for IPv4 is TOS, or type of service. Type of service is 8-bit and it uses 3-bit for IP precedence and 4 bits for TOS, or type of service, with the last bit not being used at all. Having said that, the 4-bit TOS field, although defined, has never been used. So that leaves only 3 bits for IP precedence, and that's it. IP precedence, a 3-bit field used to identify the level of service a packet receives in the network. Later, because the type of service bits are typically not used, those 4 bits, the IP precedence field can be extended from 3 to 6 bits by using 3 bits from the TOS field, 3 bits out of those 4 unused bits. And this new field is called differentiated services code point. So D for differentiated, S for services, C for code, and P for point, DSCP. Having 6 bits length, that gives you 2 to the power of 6 possible values, or 64 values that can be used with DSCP in order to prioritize traffic. Although there are 64 possible DSCP values, only 14 are used typically. So remember, DSCP is a 3-bit expansion of IP precedence with the elimination of the type of service bits, TOS bits. With differentiated services code point DSCP, a 6-bit field is used to identify the level of service a packet receives in the network. So to sum up, we have 2 options, either IP precedence or DSCP. If we have IP precedence, a 3-bit field is used in order to identify the level of service. If we use DSCP, a 6-bit field used to identify the level of service a packet receives in the network. Next, IPv4 header is total length. Specifies the length of the IP packet that includes the IP header plus the user data. So total length, as the name total suggests, includes header plus data, user data. The length field is 2 bytes, so the maximum size of an IPv4 packet is 2 to the power of 16, so the maximum size is going to be 65,535, 65,535. Next, 3 header fields in gray color for IPv4 are identification, flags, and fragment offset, respectively. Identifier, flags, and fragment offset. Well, as an IPv4 packet moves through the internet, it might need to cross a route that cannot handle the size of the packet. The packet, therefore, will be divided, or in other words, it will be fragmented into smaller packets and then reassembled later. These 3 header fields are used to fragment and reassemble packets. As you can see, fragmentation with IPv4 here happens with routers along the path. But remember, with IPv6, the fragmentation happens with the source. So if the packet is too large, then we inform the source or the sender, and he will take care of it and will fragment or divide the packet into smaller pieces. Next header field is time to live TTL. It is possible for an IP packet, IPv4 packet, to roam aimlessly around the internet. We don't want this to happen. If there is a routing problem, this may happen and we may have a routing loop. So you don't want your packets at the end of the day to be forwarded forever. A routing loop is when a packet is continually routed through the same routers over and over. To avoid this situation, the TTL field is initially set to a number and then it gets decremented at each hop by every router that is passed through. When TTL reaches 0, the packet is discarded. Next header field is protocol. In the layered protocol model, the layer that determines which application the data is from or which application the data is for is indicated in this field using the protocol field and the value inside it. Remember, this field does not identify the application itself, but identifies a protocol that sits above IP layer in layer 4, and that is used for application identification. So protocol header field and the value assigned to that, it identifies the layer 4 protocol sending the datagram. For instance, protocol can have the number 17 inside it to highlight UDP in layer 4, or can have value 6 to identify TCP in layer 4, or can simply use number 1 in order to show ICMP application, or can be set to 88 to represent IGRP. This protocol does not exist anymore, however. Or it can have 89, and this value shows OSPF sitting directly on the top of IP layer inside layer 4. Next header field is header checksum, a value calculated based on the contents of the IP header in order to determine if any errors has occurred in transit or has been introduced during the transmission. Next, we have options and padding. The main use of options field is primarily for testing. As the name option suggests, it is an optional field and can have variable length. So in most IPv4 packets, we don't have options, not included in most packets. One famous example, when we make use of this field in order to do extended ping in specific use case, options can be used to record route or to timestamp route. So these are different settings for option. If one or more options are used, that means that the size of IP header is no longer a multiple of 32 bits. Recall that the IHL field can contain either 5 or 6 depending on the size of IP header. The minimum is 20 bytes and the maximum is 24 bytes, so 5 and 6 respectively. IHL IP header length has to be in 32-bit increments, and that's why if one or more options are used, the size of IP header is no longer a multiple of 32-bit, and for this reason 0 bits are added in order to pad out header, so it ends on a 32-bit boundary. That's why options and padding, they vary in length from 0 to a multiple of 32 bits. If option values are not a multiple of 32 bits, then zeros are added or padded to ensure that this field only contains a multiple of 32 bits. Just to recap, we have IP header, we have seen the fields inside the header. Along with the IP header, we're going to have data. And data can be another layer 3 protocol like ICMP, or data in layer 3 can be higher layer protocol data. In turn, they can be TCP, they can be UDP. Next up is IPv6 header with 128-bit for addresses. That means we're going to have increased address space as the first feature for IPv6. Also, with fewer fields within IPv6 header compared to IPv4, we're going to have improved packet handling because we have fewer fields to handle. The third feature is that with IPv6 we do not need NAT, network address translation, because we do not need to share addresses with IPv6. Why is that? We eliminate the need for NAT because we have enough number of addresses. There are roughly enough IPv6 addresses for every grain of sand on earth, they say. So that's why we don't need NAT anymore. What are the IPv6 header fields? We start with version, the legacy from IPv4. It contains a 4-bit binary value set to 0110 that identifies it is an IPv6 packet. Then we have traffic class field. Traffic class field is equivalent to what we had TOS type of service in IPv4. Traffic class is 8-bit field equivalent to IPv4 differentiated services DS field that we had. Flow label, however, is a new header field. It is 20-bit field. It only comes with IPv6. We don't have it in IPv4. This new field, flow label, suggests that all packets with the same label, with the same flow label, they receive the same type of handling by routers. Next field is payload length. 16-bit field indicates the length of the data portion or the length of the payload of the packet. Unlike IPv4 that we had total length, we don't have that field anymore. With IPv6 we have payload length instead, and we only care about data portion size or payload size. Then we have next header. Next one is next header. 8-bit field is equivalent to IPv4 protocol field that we had. It indicates the data payload type that the packet is carrying at the moment. Hop limit. So hop limit 8-bit field replaces the IPv4 TTL field that we used to have. This value is decremented by 1 as you expect as it passes through each hop or each router. When it reaches 0, that means the packet is discarded. And then of course we have source IPv6 address, destination IPv6 address, 128-bit field identifies the sending host and the receiving host. Next step is routing. Routing happens in layer 3. This is to direct packets between hosts. For this purpose, source IP address and its associated mask address is compared with the destination IP address and its associated mask, and this process is compared against one another in order to determine if the host is on local or remote network. If the source address is 1.1.1.1/24, and if we apply the subnet mask /24 against this IP address, then this is going to tell us the network or the source network where the sending host resides in. In this case, it is going to be 1.1.1.0/24. This is the source subnet or source network within which the sending host resides. And then we have the destination address, let's say 2.2.2.2, and the subnet mask for the destination network is /24. So if we compare these two together, then we come to know that the destination subnet or destination network is 2.2.2.0/24. And if we compare this destination subnet or internetwork against the source subnet or source internetwork 1.1.1.0/24, they are two different things. They are not equal, meaning that the sender and receiver are residing on different networks. So the destination is on a remote network. In this case, the default gateway of our local network as the sender needs to be used to get to the remote network. Default gateway is already defined on hosts, either statically or dynamically with DHCP, and is used in order to route traffic out to other remote networks. How this process is happening: when a router receives a packet destined for a remote network, 2.2.2.0/24 in this case, the router has to look at its routing table in order to determine where to forward that packet. And inside routing table, we have certain information stored. A router's routing table contains all directly connected routes, firstly. Secondly, it contains all remote routes. And thirdly, it contains the default routes. So directly connected routes, these routes come from the active router interfaces. As soon as you issue no shutdown command on the interfaces, let's say on Cisco routers in this case, when you give them IP addresses and subnet mask, and then you issue no shutdown, these routes come up as directly connected routes on the routing table. Remote routes, however, those routes come from remote networks connected to other routers. How to learn them? They are either configured manually or learned through a dynamic routing protocol, an example of which is RIP or ISIS or OSPF or EIGRP or BGP, whatever it is. They have been learned dynamically through a dynamic routing protocol. And the third group is the default route that can be seen on the routing table. This is where the packet is sent when a route does not exist in the routing table. In other words, if we don't have information for the remote network in our routing table as routers, then we use the default route. If the default route is not set under the routing table, That means we're going to discard that packet because we don't know where to send it. We have not heard from this remote network neither statically nor dynamically through any routing protocols, and that means we need to use the default route, and if the default route is not set, then we don't know what to do with it, so we just discard it. If with IPv4 you issue show IP route command, then you see the contents of your IPv4 routing table on a Cisco IOS router. So the routing table shows directly connected as well as remote routes plus the default. When a router interface is configured and activated with no shutdown, then the following two routing table entries are created automatically. One is shown with C, another is shown and represented by L. C identifies that the network is directly connected and the interface is configured with an IP address and activated with no shutdown command. L, on the other hand, identifies that it is a local interface. So C for directly connected and L for local interface. This is the IPv4, the one that L is showing. This is the IPv4 address of the interface on the router, represented by L. So these two entries, L and C, this is important to remember that they are automatically added to your routing table as soon as you activate an interface of that router. You give it IP address and subnet mask, and then you provide the no shutdown command to activate it. Towards the bottom right hand side of this slide, you see this figure under R1. We have issued show IP route, and what you can see is the routing table contents for R1. Entries with C and L are the router interfaces that have been assigned with IP addresses and then they have been activated. We also have other entries shown with D. So another important piece of information shown on the routing table is how each route was learned. D stands for the Dijkstra algorithm that is used by EIGRP routing protocol. So D nominates EIGRP. For instance, it is shown that the remote network 10.1.2.0/24 is learned through EIGRP, represented by D. Next important piece of information in routing table, it comes between brackets, and this is called administrative distance and metric. What does administrative distance or AD do? AD determines the trustworthiness and rating of the route. How much trust we have put in the routing source by which we have learned about this remote network. Remember, the lower the number, the more trustworthy it is. So in this case, with EIGRP, we have administrative distance of 90, and 90 is the administrative distance for the corresponding network 10.1.2.0/24 because we have learned it through EIGRP. So the trustworthiness of the route is represented by the first number, administrative distance or AD. Next number inside the bracket represents the metric or the cost to get to that remote network. For example, 2170.112 represents the metric or value assigned to reach this specific remote network. similar to administrative distance or AD. With metric, the lower values indicate preferred routes. Next important piece of information on the routing table is the interface by which we can reach the destination. So which interface is used to reach the destination, or the outgoing interface that is coming next. 209.165.200.226 is the IP address of the next hop. So the next router to forward the packet is known via next hop information here. When a packet arrives at a router destined for a remote network, it will send the packet to the next hop address corresponding to the destination network address in its routing table, shown in orange color here. So via 209.165.200.226. Next important piece of information that you can see on the routing table for each network is when the route was last updated. 000005 is an example. Route timestamp identifies when the router was last heard about this specific network. Last but not least is the default gateway information. Here under the routing table you can see that the gateway of last resort is not set. Notice in the routing table, if a default gateway address is not set, that means if the router receives a packet for a network that is not in the routing table currently, it will be dropped, and that's it. Next up is IPv4 and IPv6 addressing. We have seen IPv4 before. We know about default gateway, the IP address of the local router's interface facing us, and we know that the default gateway acts as a taxi if we want to get to remote locations, i.e. remote networks. We know about subnet mask. Subnet mask identifies the network portion against the host portion of the IPv4 address. We are going to have mask or prefix length with IPv6 as well. Prefix length in IPv4 or IPv6 is known as shorthand method of expressing the subnet mask, meaning that the number of bits in the subnet mask set to 1 is shown as the prefix length. So prefix length equals the number of ones, written in slash notation, so followed by the slash sign and then the number of network bits. For each subnet or for each network, we are looking for 4 types of addresses or 4 different pieces of information. We want to see firstly network address, then first host address or first usable address, and then the last host address or the last usable address, and fourthly and finally the broadcast address. Let's say for 192.168.10.0/24, we know that the prefix length is /24, and that is the number of bits in the subnet mask set to 1. Then the network address is going to be host portion of this address when all zeros are set. In other words, when we have 192.168.10.0, this is the network address, the first address. The second address, or the second type of addresses that we have, is the first host address or the first usable address. It is when host portion is all zeros and ends with a 1. So we're going to have 192.168.10.1/24 as the first host address or the first usable address. And then we have the third type of addresses with IPv4. We have last host address or the last usable address. It is formed when the host portion is all ones and ends with a 0 at the end. So going to have 192.168.10.254/24 as the last host address or the last usable address for addressing a host. And then we have the fourth category or the fourth type of addresses in IPv4 called broadcast address, and that's when we have host portion all set to ones. So in other words, in this example, we're going to have 192.168.10.255/24. This is our broadcast address. We have two types of broadcast addresses with IPv4. Remember, we have direct broadcast address versus limited broadcast address. When I'm talking about 192.168.10.255/24, I'm talking about direct broadcast address for that specific subnet. So in other words, I'm addressing all nodes within that subnet. When we have 255.255.255.255, then I'm talking about limited broadcast address because I am addressing everyone in that broadcast domain. So we have direct broadcast address versus limited broadcast address, two different types of broadcasts. We do not have broadcast concept in IPv6. We will see shortly that multicast replaces broadcast in IPv6. But we have other addresses in IPv4. We have special use IPv4 addresses. We start from the first category, loopback addresses. The very famous one, 127.0.0.1. You see this instance here, but remember the special use IPv4 addresses, the first category, loopback addresses, is not only limited to this single IP address but also covers all the subnet under 127.0.0.0/8. And you see such a big waste of IP address space. The whole subnet, more than 16 million addresses under this subnet, can be used for loopback purpose, and as you would imagine, it's such a big waste. We just need one single address for loopback. In fact, loopback is there in order to be used on a host to test if the TCP/IP configuration is operational. For this purpose, one single IP address is enough because it serves the purpose locally on each machine. We issue that, and if we get replies, that means that the TCP/IP configuration on that local machine is operational. The second category for special use IPv4 addresses is linked local addresses. This is mainly used by Windows machines. It's commonly known as another word, APIPA. APIPA stands for Automatic Private IP Addressing. This is the same as linked local address in IPv4, used by Windows client machines to self-configure if no DHCP server available. The range for APIPA or Automatic Private IP Addressing or linked local addresses for IPv4 is 169.254.0.0/16. So all addresses within this subnet can be used for linked local addresses by Windows client to self-configure if no DHCP server is available. So very famous one, you see 169.254.0.1 for instance. The third category of special use IPv4 addresses covers the addresses that are used for teaching and learning purpose. 192.0.2.0/24. So all the addresses from 192.0.2.0 to 192.0.2.255, this range, all these addresses can be used for teaching and learning purpose. The early RFC 790 back to early 1980s, 1981 in particular, defines classful addressing. So internet IPv4 addresses were assigned using classful addressing, and we have 5 different classes. The first 3 are very important. Remember, this discussion, it does not exist anymore, it's obsolete, but still we need to know about it. This is important when we come to VLSM later with IPv4. In IPv6, however, we don't have VLSM, and this is known as obsolete when we discuss IPv6 addressing. For now, we have class A, class B, class C, class D, and class E. Class A starts from 0.0.0.0/8 all the way up to 127.0.0.0/8. This class A, is such a waste of addresses. It was designed to support extremely large networks. As you can see with /8, we're going to have more than 16 million host addresses for a single company that was assigned with a /8 from class A. We don't have such a big company in reality. The first octet from the left is going to have the first bit from its left set to 0 for class A, and the default mask for class A is /8, as you have seen. Then we have class B. Class B, as you would expect, starts from 128.0.0.0/16 all the way up to 191.255.0.0/16. You don't see 127.0.0.0/8. The reason is that this network has been reserved already for loopback addresses, for special use IPv4 addresses. So class B starts from 128.0.0.0/16. Class B was designed to support the needs for moderate to large size networks. So up to approximately 65,000 host addresses can be addressed with class B. Still too big for today's networks, for today's businesses. We don't need that many. So bear in mind that for class B, the first bit of the first byte must always be turned on, and so it's 1, and the second bit of the first byte is always set to 0, so it's always off. So from left to right, the first 2 bits are 1, 0. Next, we have class C, starting from 192.0.0.0/24 all the way up to 223.255.255.0/24. This is known as class C. So class C was designed to support small networks with a maximum of 254 usable addresses to be used by hosts. And if you take the first byte from the left hand side, high order byte is going to have the first 3 bits set to 110 from left. So 110 from left indicates class C, 10 from left indicates class B, and first bit from left set to 0 indicates class A. We of course have two more classes, class D and class E. IP address belonging to class D are reserved for multicasting. This is important. The higher order bits of the first octet of IP addresses belonging to class D are always set to 1110. So the first 4 bits from left is 1110. The remaining bits are for the address that interested hosts recognize. In other words, the other bits are used for different multicast classes or multicast groups. Different hosts can join or can leave different multicast groups. Class D does not possess any subnet mask. IP addresses belonging to class D, once again, they range from 224.0.0.0 all the way up to 239.255.255.255. Finally, we have class E. Class E was reserved for experimental and research purposes. Class E IP addressing, it ranges from 240.0.0.0 all the way up to 255, 255, 255, and 254. This range can be used as class E addresses. Class E, similar to class D, does not have any subnet mask, and this is important to remember that the higher order bits of the first octet of class E are always set to 1111. So the first 4 bits from left is set to 1111. Now that you see how big the address space was initially for classful addressing, you appreciate classless addressing with classless interdomain routing CIDR. So starting from RFC 1918, this number is important, classful addressing is obsolete and has not been used in the internet since the implementation of CIDR from 1993, from early 1990s. For example, while 10.0.0.0/8 was a single Class A network, it is common now for organizations to divide it into much smaller /16 or /24 networks. Also remember, a very common misconception is that a /16 subnet of a Class A network is referred to as a Class B network. It shouldn't. /16 subnet of a Class A network is not referred to as a Class B network. You should check the first few bits from the high order byte from left to right. Likewise, /24 subnet of a Class A or Class B is not referred to as a Class C network. The class is determined by the first 3 bits of the prefix, and this is important. Next up is IPv6 addresses. Next up is IPv6 addresses. IPv6 address size is 128 bits in length. Every 4 bits of which is represented by a single hexadecimal digit. So a single hexadecimal digit is equivalent to 4 bits. So it can have 2 to the power of 4 or 16 different values. Another term to understand is hexstat. Hexstat is an unofficial term referring to a segment of 16 bits or 4 hexadecimal values. So, in summary, every 4 bits is a single hexadecimal digit, and every 4 hexadecimal digit or segment of 16 bits is a hexstat. Therefore, an IPv6 address can be represented by 8 hexstat, because 8 times 16 is 128 bits. The way that we write down an IPv6 address has some conventions to consider. The first one, or rule 1, happens inside any hexstat, and rule 2 happens with a string of hexstats. With rule number 1, or rule 1, we omit leading zeros inside any hexstat. So in order to reduce or in order to compress an IPv6 address, first rule asks us to omit leading zeros in any hexstat. Rule 2 is about a string of one or more 16-bit segments or hexstats consisting of all zeros. It simply asks us to omit all 0 segments and replace them with a double colon. So a double colon can replace any single contiguous string of one or more hexstats consisting of all zeros. Next, we want to see different types of IPv6 addresses. One categorization is that we have 3 types of IPv6 addresses. Remember, we don't have broadcast type with IPv6. So we only have unicast, multicast, and a new type in IPv6 that we didn't have in IPv4 is called anycast. So 3 different types of IPv6 addresses. With unicast, of course, we have single source IPv6 address. With multicast, similar to IPv4, we have an IPv6 multicast address to be used to send a single IPv6 packet to multiple destinations. So single packet to multiple destinations. And the third and the new type of addresses that we have with IPv6 is anycast. With anycast, an IPv6 anycast address can be any IPv6 unicast address that can be assigned to multiple devices. So any unicast address that can be assigned to multiple devices. Let's imagine that we have a service, we need a service, and that service is offered by a server with an IPv6 address, anycast address. In fact, in this scenario, we don't care where that server or that machine is located. And the server side also, it wants to fulfill our request or our need as customer. So it can be assigned to any machine with the same service, and the one that is closer to us can serve our purpose. So any IPv6 unicast address that can be assigned to multiple devices is anycast address, a new concept that we have with IPv6. Then next up is IPv6 prefix length. similar to IPv4 subnet mask. Here we want to have a way to indicate the network portion of an IPv6 address. The prefix length, of course, can range from 0 to 128 in theory, but typically IPv6 prefix length for most LANs is /64. Next, we are going to talk about different unicast addresses in IPv6. Here, I have listed 6 different categories for different IPv6 unicast addresses. We'll start with the famous one, global unicast. These are globally unique and also internet routable addresses. Second category is link local IPv6 addresses. In fact, you see in practice that we have only these two to be configured on routers, and in different scenarios where we have global unicast address as well as link local address. These two together, this is what we need from IPv6 addressing. So link local is used in order to communicate with other devices on the same local link, and therefore this is confined to a single portion of the network. The important point about link local addresses is that they enable a device to communicate with other IPv6 enabled devices on the same link only, and this can happen even if the device has not been assigned a global unicast IPv6 address. So this is very important. It acts as an enabler in our network. Link local addresses, they are in the range of FE80::/10. Please note that typically it is the link local address of the router that is used as the default gateway for other devices on the link. So we provide link local address of the router interface as the default gateway, and we assign them when we specify them in all devices. How do we assign addresses, IPv6 addresses, global unicast or link local? Well, host global unicast configuration for address assignment is happening manually, configuring the IPv6 address on host exactly the same way that we do with configuring an IPv4 address. Default gateway, however, can be configured to match the link local address or global unicast address of router's interface. So we know that default gateway is the router interface towards the network that acts as the taxi to reach remote networks. Either link local address of that router's interface or a global unicast address of router's interface can be configured on hosts as the default gateway. Unlike host global unicast configuration, link local addresses not only can be established manually but also can be established dynamically. And when we have dynamic assignment of IPv6 addresses for link local, we ask routers to generate part of link local addresses on IPv6 interfaces automatically. And this automatic generation has a drawback. So in particular, we ask Cisco iOS routers to use a process that we know as EUI64. We see that later, to generate the interface ID portion for all link local address and IPv6 interfaces. And the drawback is that when you use dynamic assignments for link local addresses, you're going to have long interface ID because it's being generated automatically by routers iOSs, and therefore they're often configured statically. So a very famous one is IPv6 address FE80::1 slash link local command that you're using to configure link local addresses statically rather than letting routers generate them automatically. Next one is a loopback, an address not assigned to any physical interface, but instead it can be used for a host to send an IPv6 packet to itself for testing its protocol stack. Fourth category is unspecified address. This is very important. Unspecified address ::/128. It already sounds very strange. It is used only as a source address and indicates the absence of an IPv6 address. Fifth category, we've got unique local. You see the range here. It is used for local addressing within a site or between a limited number of sites. This means that it is similar to a private address range that we have in IPv4 under RFC 1918, and this is not intended to be routable in the IPv6 based internet. However, unlike RFC 1918 addresses, the unique local IPv6 addresses are not intended to be statefully translated to a global unicast address, so we don't have NAT, and as a result, in IPv6, unique local addresses are only used within a site. And the last category is the embedded IPv4. IPv4 embedded is in fact an IPv6 address that carries an IPv4 address in the low order 32 bits of the address. Next, we examine the structure for global unicast address. It has three different parts and it's very important. The first part is global routing prefix. Second part is subnet ID, and the third part is interface ID. So interface ID, the third part, is equivalent to what you had as host portion in IPv4 addresses, and it's the one that it gets automatically generated when we use a dynamic address assignment for link local addresses if you don't configure it yourself statically. So global unicast address structure, 3 parts: global routing prefix, it shows the network portion of the address, and global routing prefix is assigned by the provider and it is typically a /48. The second part, you've got subnet ID, and it is used to subnet within an organization. So we still have subnetting in different concept. And the third part is interface ID. This is also interesting to consider that at the moment, only global unicast addresses with the first 3 bits of 001 or 2000:/3 are being assigned. Only these. A global unicast address of 2000:/3 This is what you see a lot in practice when you're doing labs. Then we have IPv6 multicast address types. Two types of IPv6 multicast addresses. We have assigned multicast and we have solicited node multicast. With multicasting, we've got multicast groups and they are predefined. So the first category of IPv6 multicast, assigned multicast, is reserved multicast addresses for predefined groups of devices. In this category, we have well-known multicast addresses, and they have the prefix FF00 /12, and they're equivalent to IPv4 well-known multicast addresses that we used to have in the range of 224.0.0.0 to 239.255.255.255. Common IPv6 assigned multicast groups include FF02:1 when we want to send something to all nodes. This is a multicast group that all IPv6 enabled devices join, and that's what it's called all nodes multicast group. And this is very similar to the broadcast concept that we used to have in IPv4. So remember, we don't have broadcast in IPv6. Multicast in IPv6 is playing the role of broadcast in IPv4. Next important IPv6 assigned multicast group is FF02:2. It is all routers multicast group. So this is a multicast group that all IPv6 routers join. So to conclude, FF02:1, all IPv6 enabled devices join this group, and FF02:2, all IPv6 routers join in this group. We also have other well-known multicast groups in IPv6, FF02:5 for all OSPF version 3 routers, and also FF02:A, all EIGRP IPv6 routers. So EIGRP for IPv6 uses this specific multicast group. If you want to have a clue how to memorize it, remember EIGRP is an advanced interior gateway routing protocol, A for advanced, and then FF02:A. That was the first category for IPv6 multicast or assigned multicast or well-known multicast. The second group is solicited node multicast. Solicited node multicast, these are addresses that are used as a more efficient approach to IPv4 broadcast address. And as a result of this, we don't have ARP address resolution protocol as such in IPv6. Instead, we use solicited node multicast for address resolution, or layer 3 to layer 2 address resolution, thanks to solicited node multicast. So remember, these addresses are used as a more efficient approach to IPv4's broadcast address. It is used in layer 3 to layer 2 address resolution, similar to ARP or address resolution protocol is used in IPv4. Here we have solicited node multicasts that are automatically created using a special mapping of the device's unicast address with the solicited node multicast prefix FF02:00:001 FF00:/104, and solicited node multicast addresses are automatically created for every unicast address on a device. So the takeaway point for you is that this is equivalent to ARP address resolution protocol in IPv4. Next stop is stateless address auto-configuration, or what we know as a SLAC. A device can obtain its prefix, the prefix length, and the default gateway address and other information from an IPv6 router. So the whole idea of SLAC is for a device to obtain this information from IPv6 router. In IPv6, this is doable thanks to ICMP version 6. The way that a device obtains its prefix length and default gateway from IPv6 router can be divided into two phases. In phase 1, device sends router solicitation message to all IPv6 routers.